In 1929, American factory managers were being asked to buy one of the strangest materials they had ever seen. It did not look revolutionary. A piece of it could be smaller than the end of a man's thumb. It was usually brazed onto an ordinary steel tool holder, so little of the expensive material was actually visible. But when that tiny tip touched spinning, cast iron, or steel, something unusual happened. It kept cutting. A high-speed steel tool might soften as heat built at the cutting edge. This new material could work hotter. It could cut faster. It could survive jobs that destroyed ordinary tooling. It could turn hardened surfaces, abrasive castings, glass, porcelain, and materials that machine shops had learned to approach cautiously. Trade name General Electric gave it was Carbide. And in 1929, Time magazine reported that the material cost roughly $500 a pound, nearly twice the price of gold at the time. Yet the extraordinary price was not its biggest problem. The bigger problem was that American industry did not know how to use it. Thousands of carbide-tipped tools were sent to factories for trials. Many came back, some broke, others chipped. Machine operators treated them like the high-speed steel tools they had used for years, and concluded that this new miracle material was unreliable. General Electric had acquired access to a German invention that appeared capable of changing metalworking, but possessing the formula was not the same as creating an industry. That distinction would consume more than a decade, millions of dollars, new factories, new manufacturing methods, new machine tools, hundreds of experimental compositions, and an enormous effort to teach American machinists how to work differently. And when GE finally succeeded, it would create something larger than one profitable product. It would help change how factories cut metal. The story began not in an automobile plant, a steel mill, or a machine tool company. It began with a light bulb. By the early 20th century, electric lamp manufacturers had discovered that tungsten made an exceptional filament material. Tungsten could tolerate temperatures that would destroy many other metals, making it ideal for producing bright incandescent light. But before a tungsten filament could glow inside a lamp, manufacturers had to turn tungsten into extremely fine wire. That meant drawing the metal repeatedly through small holes in hardened dies, reducing its diameter step by step. The problem was wear. A drawing die might begin with a precisely sized opening, but every length of hard tungsten wire passing through it attacked that opening. As the die wore, the hole slowly became larger. The diameter of the wire changed with it. For a company making millions of lamps, that was not a minor inconvenience. It was a production problem. Diamond could make an excellent drawing die because it was extraordinarily hard and wear-resistant. But diamond was expensive, difficult to obtain in suitable forms, and hardly an ideal foundation for a rapidly expanding mass production industry. Engineers wanted something that approached the hardness and wear resistance of diamond, but could be manufactured deliberately. The search led to tungsten carbide. Tungsten carbide itself was not new. Chemists had produced tungsten carbides before the 20th century. The material was exceptionally hard, but hardness alone did not make a useful industrial tool. Pure or nearly pure carbide could also be brittle, and that exposed a basic materials problem. A cutting tool needs hardness because its edge must resist wear. But it also needs toughness because real machines vibrate, tools encounter interruptions, loads change, and cutting edges experience shock. Make a material extremely hard but too brittle, and the edge may simply fracture. Make it extremely tough but too soft, and it wears away. Breakthrough was finding a way to combine both characteristics. At the Osram Research Organization in Germany, Karl Schroeder and his colleagues were investigating better materials for drawing tungsten filament wire. They experimented with tungsten carbide powders and different metallic binders. Iron was tried, nickel was tried, then cobalt. The result with cobalt was different. Instead of trying to make a tool from one homogeneous metal, the researchers were effectively creating a composite. Microscopic particles of tungsten carbide supplied the hardness. Cobalt formed a metallic binder around them, holding the hard particles together and giving the finished material enough toughness to become useful. The ingredients began as powders. They were mixed, pressed into shape, and heated to a carefully controlled temperature. During sintering, the cobalt binder helped consolidate the carbide particles into a dense body without requiring the tungsten carbide itself to melt. This was powder metallurgy being used to create something conventional steelmaking could not easily produce. Schroeder's patent work in 1923 became one of the landmarks in the history of hard metals. But Osram had been trying to solve a lamp manufacturing problem. It had not set out to transform every machine shop in the industrial world. A larger possibility attracted Friedrich Krupp in Germany. Krupp acquired rights to the technology and developed it into a commercial material. The company gave it a name that captured exactly what it was trying to sell. Widia. The name came from the German phrase wie Diamant, like diamond. By 1926 and 1927, Krupp was bringing Widia into commercial use. The proposition was remarkable. Take a small tip made from this new hard material, attach it to a strong steel shank, and a cutting tool could operate at speeds that would punish conventional tool steel. But there was a problem hidden inside the breakthrough. Knowing the ingredients was not enough. A recipe that says tungsten carbide plus cobalt sounds simple. Industrial reality was not. The size of the tungsten particles mattered. The carbon content mattered. The purity of the powders mattered. The percentage of cobalt mattered. How thoroughly the powders were mixed mattered. Pressing pressure mattered. Humidity could matter. The sintering temperature mattered. How quickly the compact was heated mattered. How long it remained at temperature mattered. How it cooled mattered. Tiny variations at any stage could produce a material with different hardness, different porosity, different toughness, and completely different behavior in a cutting tool. That was the problem General Electric encountered. GE already had deep connections to tungsten because of its lamp business. Through its relationship with Osram, the company had access to some of the German carbide developments for lamp manufacturing. American engineers examined the material. The potential was obvious. The reliability was not. One of the most revealing accounts appeared years later in federal court testimony. GE engineer Samuel Hoyt recalled investigating the German material after seeing it at the Osram plant in 1925. The manufacturing process, he concluded, was inadequate for what GE wanted. The carbide could be extraordinary, but it was not extraordinary every time. GE's lamp operations had tested German material and found enormous variation in wear performance. According to the testimony, roughly 1 die in 20 might greatly outperform the material the company was already using. The other 19 could be so inconsistent that the factory preferred its older dies. Imagine trying to build an industry around that. A factory manager does not care that one experimental tool can perform a miracle. He cares whether the next 100 tools will behave the same way. This distinction between laboratory performance and industrial repeatability became the center of GE's work. Beginning around 1926, General Electric committed substantial research resources to cemented carbide. The objective was no longer simply to prove that the material could work. Germany had already demonstrated that. The objective was to make it predictable. Researchers attacked the production process from multiple directions. Samuel Hoyt worked on hot pressing, combining heat and pressure during consolidation. Emery Gilson developed another method in which tungsten, carbon, and cobalt could be processed together, so carburizing and consolidation occurred in a more integrated sequence. Benno Strauss worked on prolonged ball milling to create a more uniform mixture of the powders. Other engineers studied furnaces, grain size, brazing, grinding, and the geometry of the finished tools. At the end of 1929, GE had filed numerous patent applications around the emerging technology. But the most important product of that research was not necessarily any single patent. It was accumulated manufacturing knowledge. That difference would later become important in court. For the moment, however, General Electric faced another issue. Krupp controlled important German rights and had begun selling Widia commercially. GE had its own developments and patent interests. Both companies could see the same market forming, so they negotiated. In November of 1928, General Electric and Krupp signed a major agreement covering their carbide patent interests and commercial arrangements. That same year, GE helped form the Carbide company to handle the new business. Carbide would become the American identity of cemented carbide for generations of machinists. But in 1928, it was far from an established industry. It was an expensive experiment. There was a simple reason the first carbide tools used only a small insert or tip. Nobody could afford to make the entire tool from carbide. Conventional steel shank provided strength and structure. A tiny carbide blank was brazed into the cutting end. The valuable material was placed only where its extraordinary hardness was needed. Even then, the price was staggering. In early 1929, Time described Carbide and Whittier competing for acceptance in American industry, while the material sold for about $500 a pound. That price could be justified only if the carbide did something dramatically better than steel. And sometimes it did. The first customers discovered an uncomfortable truth. You could not simply place a carbide tip into the same machine, use the same geometry, copy the same feeds and speeds used for high-speed steel, and expect success. Carbide wanted to be treated differently. Its advantage appeared when the machine was rigid enough to exploit it. A carbide tool could tolerate higher cutting temperatures, but its lower toughness meant it disliked chatter and shock. A worn machine tool with loose bearings, flexible work holding, or excessive vibration could destroy a brittle carbide edge quickly. This meant GE was not merely selling a better cutting tool. It was asking factories to reconsider how they machined metal. And many factories were not interested. In 1929, Carbide shipped thousands of carbide-tipped tools for industrial trials. Then they started coming back, by the thousands. The reports were discouraging. Tools chipped, tips broke, operators complained. Factories that had been promised dramatically higher cutting performance saw expensive pieces of material fail before their cheaper steel tools would have. Carbide scrapped thousands of dollars worth of returned tooling. The invention was technically impressive and commercially close to disaster. This is where the story could easily have ended. Many industrial technologies fail in exactly this way. A laboratory achieves remarkable performance under controlled conditions. A company launches the product. Real customers expose everything the laboratory did not anticipate. Management decides the market is not ready. The project disappears. GE did something else. It kept spending money. The company treated the failures as information. If a carbide tip broke at the joint, improve the brazing. If it fractured because the steel support flexed, redesign the holder. If the edge chipped because the cutting geometry was wrong, change the geometry. If one batch performed differently from another, improve powder preparation and furnace control. If a customer destroyed the tool by running it like high-speed steel, teach the customer how carbide needed to be used. This last point mattered enormously. Carbide gradually became not just a material supplier, but an engineering service. Its people went into factories. They helped select cutting conditions. They trained operators. They designed tools around particular machining operations. They studied why carbide failed and then redesigned the entire process around keeping the cutting edge alive. The product and the knowledge began growing together. In 1930, the manufacturing process improved. A better way of sawing carbide helped reduce production time. Powder molding methods expanded the shapes that could be produced. Wire drawing dies began demonstrating the kind of wear resistance that had originally attracted engineers to carbide. One mill using carbide dies reportedly reduced scrap dramatically. Slowly, the failures produced rules. Carbide needed support. Carbide needed rigidity. Carbide needed controlled geometry. Carbide could cut much faster than steel, but only when the rest of the system was built to take advantage of that speed. Then came the Great Depression. It was almost the worst possible environment in which to introduce a labor-saving industrial material. Factories were closing. Production volumes were collapsing. Unemployment was enormous. Machine shops were reluctant to buy expensive new tooling, especially tooling whose main sales argument was that fewer machines or fewer operating hours could produce the same amount of work. Carbide continued losing money. For a period, contemporary accounts described losses running at roughly $1,500 a day. The operation accumulated a deficit above $1 million. GE, nevertheless, continued development. And that persistence created one of the strangest periods in the history of the material. The company experimented relentlessly because it had no choice. Carbide was too expensive to compete as a commodity. It had to solve problems ordinary tooling could not solve economically. In 1931, Carbide produced 25 experimental carbide grades. 23 were eventually discarded. That ratio tells you something important. There was no single magical formula called carbide. Different jobs demanded different combinations of hardness, toughness, grain size, and binder content. Grade optimized for abrasive cast iron might behave poorly against steel. A composition tough enough to survive interrupted cutting might not provide the maximum wear resistance needed elsewhere. Every application became an experiment. Then the automobile industry gave carbide the opening it needed. By the early 1930s, automobile engineers were pushing materials and manufacturing processes in directions that created new machining problems. Brake drums provide a good example. Their inner friction surfaces needed consistent machining, but the cast iron could be abrasive and difficult on tools. Carbide could withstand the wear much better than conventional tooling. Another challenge came from aluminum pistons containing silicon. The alloy had useful properties for higher speed engines, but silicon particles made the material extremely abrasive to cutting tools. Again, carbide had an advantage. This was the beginning of a change. Carbide was no longer asking factories to believe in an exotic German-derived material. Factories now had specific production problems for which carbide could provide a measurable answer. A tool that cost dramatically more might still be cheaper if it lasted many times longer. A cutting edge that allowed a lathe to run faster could increase the output of an entire machine. And once that happened, the economics changed completely. Consider what happens inside a factory when a cutting tool becomes 3 or 4 times more productive. The benefit does not stop at the tool. A part leaves the machine sooner. That machine can process more parts per shift. The factory may need fewer machines for the same production target. Floor space becomes available. Labor can be reassigned. Work-in-process inventory falls. The bottleneck moves somewhere else. A tiny carbide insert can therefore change the economics of an entire production line. By 1934, automobile manufacturers were reportedly using cemented carbide in hundreds of machining operations. GE engineers had also developed diamond-impregnated grinding wheels capable of finishing carbide more effectively, making it possible to grind thin sections without destroying them. Carbide was creating an industry around itself. Special grinding equipment, stronger tool holders, different lathes, different feeds and speeds, different operator training, different production planning. The cutting tool was forcing the machine shop to evolve. In one 1935 example recorded by General Electric, 4 machines equipped with carbide tools were able to perform work that had previously required 16 machines while machining cast iron refrigerator components. Another manufacturer avoided tens of thousands of dollars in additional equipment while machining truck brake drums. These were the kinds of numbers that finally changed minds. Factory managers did not need to understand powder metallurgy. They understood machine hour cost. And the greatest victory for carbide may have been the moment machine tool builders stopped treating it as an accessory. Early machine tools had been designed around the capabilities of steel cutting tools. Their spindle speeds, bearing systems, frames, power, and rigidity reflected what those tools could tolerate. Carbide changed the limiting factor. If the new cutting edge could survive far higher speeds, then the machine itself became the restriction. So machine tool builders began producing stronger and more rigid equipment capable of heavier cuts and greater spindle speeds. This is an important point because it explains why the invention itself was only half the story. Germany had created an extraordinary material. General Electric and its competitors were building an industrial ecosystem capable of exploiting it. The difference is similar to the difference between inventing a powerful engine and building the transmission, fuel system, roads, service network, and production line required to make that engine useful at national scale. Carbide needed its own infrastructure. GE spent the 1930s building it. The company trained enormous numbers of industrial workers and engineers in how to use the material. In 1936 alone, a wartime GE account later claimed that training courses reached around 10,000 people in industry. At the same time, Carbide continued lowering prices. The original pricing had been extraordinarily high. Over successive reductions, the cost of standard carbide blanks fell substantially. More customers could justify trying them. More applications generated more experience. More experience led to better grades. Better grades opened more applications. Feedback loop finally began working in Carbide's favor. And then, in 1939, GE opened a new carbide plant in Detroit. That location mattered. Detroit was not just another American city. It was one of the greatest concentrations of mass production machining on Earth. Automobile factories consumed cutting tools on an enormous scale. Engine blocks, brake drums, transmission parts, pistons, shafts, gears, and countless other components had to be machined faster, cheaper, and more consistently. Carbide was moving directly into the center of American production. The new plant helped push the technology out of what GE later called the cut-and-try stage. For the first time, carbide cutting tools themselves could be mass-produced on a much larger scale. And in 1940, after roughly 12 years of effort, the Carbide operation finally made its first profit. 12 years. That number may be the most important number in this story, because it shows how misleading the word invention can be. Schroeder's breakthrough had occurred in Germany in the early 1920s. Krupp had commercialized Whittia years before General Electric earned a profit from Carbide. The chemistry was known, the patent existed, samples existed, tools existed. And yet creating a dependable American carbide industry still took more than a decade. The missing technology was not one formula, it was process control, tool design, manufacturing scale, customer training, application engineering, machine rigidity, grinding methods, quality control, distribution, and thousands of failures. Then came the Second World War. For this story, the war is not where carbide begins. It is the moment the industry that had already been built was suddenly tested at enormous scale. American factories now had to machine artillery shells, aircraft components, engines, vehicles, dies, gauges, and an almost unimaginable quantity of industrial hardware. Machine time became strategic. A cutting tool that allowed one lathe to produce more components per hour was no longer simply reducing factory cost. It was increasing national production capacity. Carbide production expanded dramatically. Contemporary GE material claimed that output rose roughly 45-fold between the late 1930s and 1942. Carbide helped machine hard alloys and abrasive materials at speeds that would have been difficult with conventional tooling alone. Britain, cut off from normal German supplies after the war began in Europe, also benefited from carbide production outside Germany. But the war also brought attention to something much less flattering. Business arrangements that had helped GE obtain the technology were becoming politically explosive. Remember the 1928 agreement between GE and Krupp. It was not simply a technology license. Over time, the companies created arrangements involving patents, territories, prices, imports, exports, and sublicenses. GE and Carbide controlled major American patent interests. Krupp controlled its own technology and international position. Companies had incentives to cooperate rather than fight expensive patent battles. But cooperation between two powerful competitors can move from licensing into something else. Carbide developed detailed pricing systems. Licensees were required to follow established prices. A supervision organization monitored violations. The agreements between GE and Krupp eventually divided important geographic markets. Krupp withdrew from direct competition in the American territory under later arrangements, while GE accepted limits on where Carbide could export. What looked from one perspective like an organized system for developing a difficult new industry looked from another like competitors dividing markets and controlling prices. The United States government chose the second interpretation. And there was another irony. Just as GE's carbide business was becoming technologically successful, the legal foundation beneath some of its patents began to weaken. In 1940, during a patent infringement case in Michigan, a federal judge examined the history of cemented carbide in extraordinary detail. The ruling complicated the heroic version of the invention story. Schroeder had made an important contribution, but earlier patents had already explored tungsten carbide, metallic binders, pressing, and sintering. The court concluded that several patents being asserted by GE and Carbide were invalid in light of prior art. More interestingly, the judge emphasized something that actually strengthened the industrial part of GE's story. Commercially successful material had required numerous refinements that the early patents did not teach. Powder purity, particle size, exact carbon control, storage conditions, mixing, pressing pressure, heating cycles, sintering time, cooling. Those details had been worked out through years of practical development. In other words, the court was saying that the success of carbide did not belong neatly to one patent or one inventor. The invention had evolved. Germany had provided the decisive early breakthrough. Krupp had built Whittia into a commercial material. GE engineers had added manufacturing processes and applications. Competitors had added their own improvements. The industry was becoming larger than the patent portfolio that had originally tried to contain it. The antitrust case went even further. A federal indictment filed in 1941 accused General Electric, Carbide, Krupp, and individuals connected to the companies of violating American antitrust law. The case was delayed by the war. It was finally decided in 1948. The court examined years of contracts, licenses, price manuals, territorial arrangements, competitor purchases, and enforcement practices. The judgment was severe. The court found the defendants guilty on the charges before it, concluding that the system had crossed the line from legitimate patent exploitation into monopolization and unlawful restraint of competition. It is tempting to simplify this part of the story. One version would cast GE as the heroic American company that rescued a German invention and built an industry. Another would cast it as a monopolist that used patents to control an emerging market. The historical record supports something more complicated. GE really did spend years solving manufacturing problems. It really did lose money developing carbide. It really did create tooling, production methods, training systems, and applications that helped make cemented carbide practical across American industry. And the company also participated in agreements that a federal court later found violated antitrust law. Both things can be true. Industrial history is often like that. Organizations capable of investing enormous amounts of money in uncertain technology are frequently the same organizations powerful enough to shape the markets around the technology. Carbide survived the legal battles because by then the material no longer depended on carbide alone. A genuine American industry was forming. One of the most important competitors emerged in Pennsylvania. Metallurgist Philip McKenna developed a tungsten titanium carbide material designed for cutting steel and founded the business that became Kennametal in 1938. The name itself came from the new material. Kennametal would grow into another major American cutting tool company. That mattered because cemented carbide was no longer simply a licensed German technology manufactured by one American corporate system. It had become a field. Different companies developed different grades. Tungsten carbide could be combined with other carbides. Binder percentages could be changed. Grain sizes could be engineered. One composition might be optimized for cast iron, another for steel, another for abrasive wear, another for shock resistance, another for mining, another for drawing wire, another for forming metal. The industry moved from asking whether carbide worked to asking which carbide should be used for a particular job. That is the moment a technology becomes mature. After the war, carbide continued moving into applications that had little connection to its original purpose. Remember where the story began. A drawing die for tungsten lamp filament. Now carbide entered rock drilling, oil and gas equipment, mining tools, industrial wear parts, metal forming dies, powder compaction, nozzles, rolls, cutting inserts, components exposed to erosion and abrasion. General Electric's carbide operation expanded into new materials as well, including cemented chromium carbide and other engineered compositions. By the early 1950s, GE was investing in additional carbide manufacturing facilities in Michigan. Carbide was no longer an exotic tip that salesmen had to persuade skeptical machinists to try. It had become ordinary industrial infrastructure, and ordinary may be the greatest compliment an industrial technology can receive. Nobody walking through a modern machine shop stops in amazement because a lathe uses a carbide insert. They expect it. A modern cutting insert may be a carefully engineered shape with chip breakers, complex geometry, multi-layer coatings, and a substrate designed for one specific combination of workpiece, speed, feed, and cutting condition. The insert can be indexed when one edge wears. Its composition may be the result of a century of materials engineering, but underneath all of that refinement remains the same fundamental idea that made Schroeder's experiments so important. Extremely hard carbide grains, a tougher metallic binder, a composite created through powder metallurgy, hardness where hardness is needed, toughness where pure carbide did not have enough. In 1987, the old GE carbide business was acquired by Seiko. The corporate name changed, ownership changed, and the cutting tool industry continued consolidating and globalizing. But Seiko's North American history still traces its Detroit roots back to the carbide operation established in 1928. The lineage survived. So did the industry GE helped build. And this brings us back to the strange little cutting tip that American factory managers were being asked to buy in 1929. At the time, it seemed almost absurd. Material costing hundreds of dollars per pound. A material so brittle that using it incorrectly could destroy it instantly. A material that sometimes required stronger machines just to exploit its capabilities. A material whose early trial tools returned to the manufacturer by the thousands. It did not look like the foundation of an industry. GE eventually understood something that matters far beyond carbide. An invention is not an industry. An invention can be a patent, an experiment, a remarkable sample, a piece of material that works perfectly once. An industry begins when the thousandth piece works like the first, when workers know how to use it, when machines are designed around it, when suppliers can make it repeatedly, when customers know what it is worth, when failures have been converted into standards, when the process becomes predictable enough that nobody thinks of it as experimental anymore. Germany produced the breakthrough that made modern cemented carbide possible. Krupp recognized its commercial power and gave the world Whittia. General Electric took that technology into American laboratories and discovered that the hardest problem was not proving carbide could cut metal. The hardest problem was making it cut metal reliably, economically, and repeatedly in thousands of different factories. That took 12 years before carbide even turned a profit. And by then, the small German solution to a light bulb manufacturing problem had already begun changing the design of American machine tools, the economics of mass production, and eventually the way modern industry cuts almost everything made of metal. The invention was German. The industry that grew around it became global. But one of its most important transformations happened in American factories, where General Electric discovered that making a revolutionary material was only the beginning. The real work was teaching an entire industrial system how to use it.